Hi. So far in your studies, you should have covered all the basic fundamentals about how a tire is built, how they're rated and sized and that type of thing. We're going to look at some of the details that were not mentioned or perhaps glossed over here. So here we go with our tire fundamentals mini lesson. Centrifugal force. Now, centrifugal force is just one of those, laws of physics. Things work the way they work. But there's something to consider here. The faster you spin a tire, the more force is applied to the tread. So if we look at this, we can consider the stone in this drawing to be the tire tread. We can consider the string to be the cords in the sidewall of the tire, and the hand here, basically that'll be our axle that we're rotating around. So the faster you spin this, the more load is applied to the string. At some point, if you spun it fast enough, the string would break and the stone would fly away. So you can kind of understand from that, hopefully, why there's a speed rating on tires. So you'll find that the tire will want to stretch outwards the faster it spins. A less expensive tire can be made from lower quality materials, and if you overspeed it, it can actually come apart. So there's reasons for speed ratings and things. Okay, so friction. Friction is an odd kind of thing. So just to read through this, the force resisting the relative motion between things in contact with each other. So there's a definition for you. So typically friction converts the force creating the motion into heat. So if you kind of picture rubbing your hands together like this, if you rub them together really fast, they start to get warm. So anytime you rub two things together, you generate heat, and it's converting that energy of motion into heat. So things have a coefficient of friction. It's dependent on the type of materials and the force pressing them together. So things that slide easily have a low coefficient of friction. So you can think of a hockey skate on ice. A little push and you just glide along for a long distance. Things that do not slide easily have a high coefficient of friction. So you can think there, if you take a piece of gum and stick it on the sidewalk, if you push it into the sidewalk, you can't make that gum slide along. It's stuck there. That's a high coefficient of friction. So as in that thought experiment, lubrication can dramatically reduce friction. So you can think of that in the case of tires and things. You can think of that as rain or snow on the road. That rain or snow acts as a lubricant between the road and the tire, and that will dramatically change the amount of friction that the tire has on the road. So things to consider. Would a hard or soft rubber tire grip the road best? If you think about that for a second, that would be equivalent to asking the question about either the hockey skate or the gum. The hockey skate doesn't grip the road because that material has a low coefficient of friction, or that interface has a low coefficient of friction. The gum, however, would stick really well. But which one would last longer? Fact of the matter is, the stickiest tire may not be what you want on your car. You may not want the absolute best traction because it may tend to wear out in a big hurry. You don't want to buy new tires every 2 days. So we'll continue. Rolling friction is a little bit of a different animal, and sometimes referred to as rolling resistance. It explains why a tire doesn't roll forever, right? So in this picture you'll see here the tire is deformed as it rolls along the ground. So if you look at that, generally speaking, the more air, and this is a bit of a blanket statement, but the more air you put in a tire, the easier it will roll, and the less heat it will generate because the rubber in the sidewall and the cords and the structure of the tire isn't flexing as much. Conversely, if the tire is underinflated, it flexes a lot, and that flexing will generate heat. Okay, so friction. You've got static friction and kinetic friction. Friction goes on forever. So if we look here, we see our static friction. There's no movement. Here we're applying some force. You have to apply a significant amount of force before things start to move. Once things move and you get one thing sliding against each other, you're into the kinetic friction area. So you see we're applying force here, but we have no movement, and then at this point, we get movement, and the amount of friction between the two things drops dramatically. So that is basically, you can translate this directly to the grip of the tire on the road. If the tire is in contact with the road and the tread is gripping the ground, you can have a relatively high amount of traction. But as soon as the tire starts to spin or slide on the road, the amount of grip available drops dramatically. Okay, so you have this much traction if there's no sliding. You have this much traction if there is sliding, significantly less. Okay, internal friction, more friction. So the force definition would be the force resisting the motion in a solid material as it deforms. So it generates heat, and this can be bad. So in the case in this picture, you see the low tire pressure allowed the tire sidewall to flex excessively. It overheated and it failed. Right? So in this case, because the tire was flexing so much for so long, generated more heat than that tire assembly could stand, and it just simply came apart. Okay? Internal friction can also be leveraged to improve traction. So in this case here, we have the case of Formula One race cars. Formula One race car rain tires. Now these things have relatively large and tall blocks of rubber, and it's soft rubber as well. When these tires are driven around the track, that rubber will tend to flex quite a bit. And that helps the tire warm up and soften to maximize the traction as much as possible. Now, the reason that for all the grooves is to displace the actual water, so we can warm up the tread, and it can cut through the water down to the asphalt underneath and give a good amount of traction. Okay, so slip ratio and coefficient of friction. So the C of F, coefficient of friction, is not the same on every surface. So the graph below does not include hydroplaning, and we'll discuss hydroplaning in a little bit. Okay, and neither does it. Well, it does to some degree point out piling, so we'll look at that. So if we look at this, the higher the number, so this is our coefficient of friction. So the higher the number, the more traction you have, right? And going this way on the scale, that's the amount of slip you have. So in this case, we build up to about here, just under 20%. A slip rate is the maximum amount of grip you can get. Previously I said, static friction, kinetic friction. What actually happens here is with a very small amount of slip, you're scuffing rubber off, you're tearing little pieces of rubber off the tire. That exposes, and it warms the rubber, and it exposes fresh, clean rubber to grab the ground. So you do get an improvement up to a point. After around 20%, you start to see that fall off. And this is typically, these numbers are typically quoted for acceleration and braking loads. You lose, the loads are different when turning. You lose the ability to steer the vehicle somewhat if you have slip while turning. Okay, so this is acceleration and deceleration primarily. You see, if we wet the road, that we don't have the same amount of traction. If we look at snow, we see we have significantly less traction, but we get this kind of a neat effect right here. The traction goes up as we get to 100% slip, meaning that the wheel is locked. It's no longer rotating. The vehicle's moving, the brakes have locked the wheel, and our traction actually goes up. That is what we looked at here, piling. Okay, so this effect happens in gravel, in sand, and in snow, any kind of loose surface. If you lock the wheel, it actually piles the surface up in front of the tire, and it will actually assist the slowing the vehicle down. Those loose surface conditions are the only ones where locking the wheel will stop a vehicle quicker. Wet asphalt, anything, and anything that won't pile in front of the tire, you're better off maintaining the traction or maintaining the wheels rolling. Think of anti-lock brakes there. Okay, if we look here, ice in this graph, it's the poorest coefficient of friction here, and you can see that and your acceleration, deceleration, and cornering capabilities would be dramatically reduced if you were driving on ice. Okay, slip ratio, coefficient of friction. It may not be consistent between braking, accelerating, and steering. So we mentioned this a little bit earlier, but this friction coefficient for curve or cornering force, you see that our amount of traction drops. The more it slips, the less ability we have to turn. And here you see for our braking and acceleration loads that they match the previous graph. So right here around 20% is where you have the maximum capability to accelerate and decelerate. But if you think of turning, you can only turn the steering wheel so far. And the more the wheels are slipping, the less the vehicle is actually turning. Okay, so the loads are a little bit different depending on which direction you're applying them. So we'll look at tread design elements, and this has been covered before, but we're just going to kind of review it here. So you've got something like this as a rib. Generally speaking, a rib in a tire is good for directional stability, runs quiet. It doesn't give you much acceleration and accelerating and braking traction to speak of. Tread blocks. So these blocks can be arranged in any number of ways, but you can see that the tread surface is kind of built up of rubber blocks. So they have spaces in between, grooves right here. So a groove would run around the tire. You have the grooves running out this way laterally to help clear water from underneath. And you have very small cuts in the tread, and those cuts are called sipes. They will allow the tread to actually open up and grab a hold of the ground a little bit. Okay, and then we have all the construction stuff which you have seen previously in other lessons leading up to this. Okay, so tread compound. You got many different blends of rubber, so it's not just one type of rubber that a tire is made out of. There's different materials used for different places on the tire, and every manufacturer will use slightly different blends, and every manufacturer probably uses several different blends for different tires depending on the application. So just some general statements here. This isn't written in stone, but generally soft rubbers tend to provide good grip. Excuse me. They flex a lot. The tread might squirm, so the tread blocks might move around. It gives you less of a positive feel on the road. They tend to consume more fuel because they have a little more rolling resistance. The softer rubber will flex more on the ground, therefore it generates more heat, and that heat represents the amount of energy you lost trying to make the tire rotate. So they do tend to run quiet, ride smooth, because they're flexible. They generate internal heat, which is possibly a source of overheating in some applications. They tend to have a short lifespan. They tend to wear out faster. So it's got positives and negatives. Hard rubbers, they tend to provide less grip. They tend to slide easier on asphalt, and sometimes even worse on rainy asphalt. They flex less, so they tend to use less fuel. All right, it's the opposite of the soft rubber. They might be noisier or ride harsher. That does depend on the tread design, though. They tend to run cooler, again, because they're not flexing, they're not generating heat, so they tend to run a little cooler, and they tend to have longer lifespans. Now, there's a caveat here that these are generic statements. There are some high-tech rubbers that break some of these rules. Okay. Tread width. So J-rod, by the way, J-rod, in case you haven't heard these yet, that's John's rule of thumb. So their generalizations can be affected by tread design and compound. So generally a narrow tread, so a tire that has a narrow tread on it, tends to be good for fuel economy. But because it's narrower, there's less surface area in contact with the ground, so you have less traction. They're good as far as hydroplaning. Hydroplaning is, we didn't expand on that yet, but hydroplaning is when you have a significant amount of water built up on the road and the tire will actually ride up on top of the water. That means you have essentially zero traction. Tires don't work on water, they work on the asphalt under the water. Okay, so the narrower the tire, the easier it cuts through the water, basically. They tend to be good in slush and light snow for some of the same reasons. They cut through that overburden of snow or slush down to the road beneath and give you reasonable traction. In deep snow, it can be a problem though, because you may need a wider tire in order to get kind of a flotation effect to get you up over the snow. In very deep snow, these can just cut through, and if they can't actually reach the ground before the undercarriage of the car is sitting on the snow, then you're stuck. They can be poor off-road. Now, the reason for this is they have what you'd call a high contact pressure. So that means that a small tire is expressing the vehicle weight over a small area. And when you get a movable surface like dirt, that means that the tire can cut down into the ground quite a bit. Now, if you think of, if you ever watched a tractor on a golf course or something, you see they have fairly wide tires, and that's to distribute the weight over a larger area so that it doesn't damage the ground. Okay? Some conditions, narrow tires are actually good off-road, but generally speaking. Okay, so wide tread. Poor fuel economy because you have a higher rolling resistance. There's more rubber flexing in contact with the ground. You tend to have better traction though because you have a wider, bigger contact patch. Poor hydroplaning resistance. So again, with a wide tire, it will roll up on top of and trap more water between the tire and the road. So it's easier to hydroplane with wider tires. Again, with light slush and snow, they tend to ride up on top of that and you lose traction. And deep snow, they can help prevent you from getting stuck because it'll lift the whole vehicle up off the ground, again, because of that whole contact area kind of deal. And they tend to be good off-road. Again, you can think of that, the tractor on a golf course, big wide tires, it doesn't dig up the ground. Okay, so what's the best tire? For what? All right, so let's have a look at some examples and we'll see if we can kind of get a sense of what's best for what application. All right, so here we have a DOT legal road race tire. So DOT legal tire means you can put it on the road. Honestly, you wouldn't want to drive a car with these. Anything that's on the road will prevent this rubber from getting to the ground. However, in perfect conditions, like a racetrack, that rubber is soft, flexible, and there's a large amount of it to contact the ground and generate a lot of traction. But as the note says here, they're virtually useless in anything other than ideal conditions. There are cases where people have gone driving around with drag slicks on their street car and a light drizzle and they lose control of their car at like 15 miles an hour. They just ride up on top of the rain and skate around like crazy. So they're not really suitable for street use. Okay, so a performance street tire. These can be similar to the tread compound or the rubber in the compound of the previous tire, but they have a lot more tread to them. So they've got tread blocks and grooves and things in there that will allow the tire to displace some moisture. The tread tends to be fairly short, so it's not very deep. That helps with preventing tread squirm, so you get a positive feel on the ground. And if you could kind of picture, if you had a tread this tall, you could turn the wheel, and the tread might stay right here, and all the flex would be in the rubber itself. That's kind of what we're talking about with tread squirm. You get a lot of flex in the tread itself, and it doesn't feel as stable as it should. Now, so this tire might feel more stable, give you good traction, be able to handle some moisture on the road, that type of thing. But because the tread material is thinner, they don't tend, and it's soft, they don't tend to last that long. Okay, in snow and things, typically not very good. Okay, so here's your kind of a regular all-season radial. The all-season tires, you can see the tread. It has some sipes. It has some tread blocks. It has some grooves. It's kind of a general tire. All right. So it's suitable for most seasons. people do use these for all 4 seasons, but in Canada, it's very common that you want to switch to snow tires. The tread is just not aggressive enough to handle any deep snow at all. And when I say deep, like, it's not uncommon to get 6 or 8 inches of snow, and this thing would have a problem with that. However, it works pretty well as a general all-around tire for the other 3 seasons of the year. If you're in an area that doesn't get much snow, you can get through the whole year with them without too much difficulty. So, fuel efficient street tire. So here, if we look at this, the treads tend to be a little narrower, tend to be a little bit harder rubber. The construction of the sidewalls and things like that tend to be stiffer. All that is to prevent some flexing. But your tire does form part of your suspension. So if you're preventing the flexing, that means you're transferring the road vibration thing right up into the chassis. So you tend to get maybe a little bit harsher ride. It's a trade-off. Save some fuel, feel a little more bumps inside the car. But they're generally in the all-season radial type tread. Okay, snow tires. With the snow tires, you can see that the blocks are built a little more aggressively, larger gaps between the blocks, so we can displace some snow into those gaps. They have lots of sipes, lots of cutting edges to grab a hold of movable surfaces. So they're also made out of a fairly soft rubber. So that rubber will, in cold conditions, it doesn't get that hard, and it'll comply to surfaces and try to grip everything as much as possible. So a couple things to note as well. In that compound, you do find some manufacturers putting some special processes into the tread compound itself. They'll put grit like sand or cork into the tread, just so that if you get down to an icy surface, there's something gritty to grab all the ice. Some manufacturers also make the tread rubber kind of foamy, so that when it cures, there's all kinds of little air pockets, and when the tire wears, those air pockets form little suction cups to try and grab all of the ground. So there's a lot of tech that's gone in to try and make the snow tires work well in the winter. That doesn't necessarily mean they work well in the summer, though. Typically, all those things that go to making it grip the ground in the winter make it wear quickly and make noise and whatnot in the summer. So snow tires, although they do provide a definite improvement to vehicle performance in the winter, they typically are not so good in the summer. Okay, so we have here this type of tire you might find on a delivery van or a highway tractor or something like that. It's a ribbed tire, so the tread has very few blocks on anything. Mostly it is ribs. So these are great for low rolling resistance. In the tread in this application, the tread is fairly deep, so it lasts a good long time. So you get low rolling resistance, good fuel economy, long lasting, all that kind of thing. Not so great in snow or anything like that. Without cuts across the tire, it's hard for it to displace anything. But if you're going to put a lot of miles on the highway delivering things or something, a tread designed like this works very well for you. I find fleet vehicles and things might use something like this. Okay, light truck all-season tire. All the same characteristics you'd see in the previous passenger car all-season tire. But the sidewalls and things like that are more sturdily constructed so they can carry a heavier load. Right? All-terrain tires. Now we're getting into something that this might be used on a, say, a four-wheel drive pickup or something like that. So an all-terrain tire like this is fairly commonly used. With a tread this aggressive, you'll find that it's going to be noisy, and they work acceptably on asphalt. They work far better than an all-season radial or something off-road. So your compromise moved from road performance to off-road performance when you select a tire like this. They can be used on trucks all year long. You'll no doubt see them around. A pickup truck that going down the highway in the middle of the summer with a set of tires like this. And if you're driving along beside one, you'll hear the tires rolling. They tend to be quite noisy. Okay, light truck, off-road, and mud tire. Here the the way the tread blocks are arranged, you get more across the tire, so you can get more linear acceleration, so you can accelerate and brake better in very loose grounds. These tend to wear funky, make a ton of noise, but they work even better off-road. So again, you've moved your compromise now from fuel economy and durability and roadworthiness to better performance off-road. Okay, so we're getting to the end here. So do you get what you pay for? Well, this is kind of interesting. We have a little just a cross-section picture of a tire here. If you look at this, you see this is your section width, right, to the sidewalls. It is not uncommon that a less expensive tire actually has less tread up here. So you might have a less expensive tire. Let's just make a little drawing. So you might have a less expensive tire where this is your last tread block, and that doesn't exist. Okay, so this here and this here may not exist on a less expensive tire. On a more expensive tire, the tread blocks might come out farther. Okay, now if you think about this, if you were a tire manufacturer and your goal was to build an inexpensive tire, one of the ways you can cut the price is to use some lower quality bits and pieces, different materials, probably not as good a tread compound, it's compound rubber, and also you can use less of it. So you can use 5% less rubber in building a tire. You've cut the cost for that tire by 5%, so you can sell it for less. If you have a tire that's oriented more towards high performance, typically the customer is going to pay more, and what you're targeting there is better performing tire at the cost of spending more money up front to get it, right? So when you look at tires, if you're shopping for them or a customer is asking your advice, you will notice that there are some significant differences. Some tires of the same size, you can find a tire for $59 or $359. They're not the same tire, and in some cases you do get what you pay for. Okay, it's been fun. I hope you learned a little bit, and we'll see you in class.